So if you look at what's happening on this assignment, right? So, and let me, and some of you have asked about this. If you look at like this value of A plus 2B yields 2C, and if all you were asked to do was write the equilibrium expression, okay, which would be uppercase K. If that's all you were asked to do, you would go, oh, K is going to equal the products, C, squared, right, divided by A times the concentration of B squared, okay? So if you're just asked to write, and this is going to be uppercase K, not lowercase k. This is uppercase K. So this, and this only works when you establish a reaction that has an equilibrium point to it, okay? Like I wouldn't write this for like the combustion of hydrogen and oxygen, because hydrogen and oxygen combine to produce water. They don't establish an equilibrium where water decomposes back and produces hydrogen and oxygen. It's a one-trick pony. You get water out of it. It doesn't establish an equilibrium. What we found is that a lot of times, especially ones involving aqueous solutions and more importantly ones that involve gases, you can establish an equilibrium where a forward reaction is going to happen and a reverse reaction is going to happen at the same time. So if all you were asked to do is express the value of an equilibrium constant, this is just going to be uppercase K, and what you would have to know is, oh, once it reaches equilibrium, what's the concentration of C, what's the concentration of A, what's the concentration of B? You would have to have these values to plug into and calculate uppercase K. So the other thing about uppercase K never has any units because of the fact that it changes so much, okay? This could be like, if this was just C, then it wouldn't be squared. So there's a myriad of ways that you can express the units of uppercase K. So we just basically says, it's not worth the effort, okay? But what you're trying to find, and this is going to be specific for a particular reaction, okay? At a certain set of conditions, you're going to establish the value of K. And it is only based upon these concentrations at that equilibrium point. Now, can you change the situation? Could you inject it with, like, for example, you have this reaction, and let's say that you have a reaction vessel and you dump in more product. Okay, well, if I dump in more product, that's going to force this reaction to go in the reverse direction until it reestablishes that equilibrium. So you can force it out of equilibrium, but Mother Nature goes, I want to go back to that equilibrium point. Same thing is true if I overload it with reactants, then it's going to force it to make more product, okay? But when you're talking about that uppercase value of K, that equilibrium constant, it is going to be based upon a certain set of conditions and a certain set of concentrations, and Mother Nature is going to do whatever it has to do to produce this value K. You can't tell speed from it, you can't tell rate from it, you can't do anything. The only thing you can do is calculate a particular value of K based upon a set of equilibrium conditions. So what we're doing on this part, that assignment from yesterday, now you're finding what's called this lowercase k, which what that's going to represent, that is a value dependent upon a set of conditions that's going to determine the rate. So this, you can't determine the rate from. You can just know, oh, it's a value. Then you can look at Q and say, hey, is it going forward, is it going backwards? But when you're looking at something like, for example, let's say something's a first order reaction, and you have R equals K times the concentration of A. This is a lowercase k, okay, which is going to have a specific set of units, which is going to change depending upon the temperature. So if you raise the temperature, oh, at a higher temperature, a reaction takes place at a faster rate. Changing in temperature will influence lowercase k. So don't confuse lowercase k with uppercase K in terms of speed, in terms of reaction rates, that type of thing. So what you should see on that first problem, when you get that value of lowercase k, it should be like 1.2, okay? That should be the value of lowercase k. Make sure that you have the correct units on that. Because if you just put 1.2, it doesn't mean anything. So what you should see on that first one is that it's first order with respect to A and first order with respect to B. So what this means is that if I double the concentration of A, I'm going to double my rate. If I double the concentration of B, I'm going to double my rate. And as long as I am running this thing at a particular temperature, then this K is just going to be a fixed value, okay? Now, what you'll see when we do a lab with this is that if you do run it at higher temperatures, higher temperatures involve faster rates. You have a bigger rate, you have to increase, then that impacts the value of lowercase k. But again, don't confuse that with uppercase k. So then, and again, what I'm looking for is that this is a process. So when you guys actually do this lab, it will involve iodine, acetone, and hydrochloric acid. What you're going to do is you're going to alter the concentrations of these values. And you're going to run these experiments under different conditions. And that's the only, if this is what you have, this is the only way you can figure out the order of these magnitudes. Basically, you're going to make everything cancel out and you're going to isolate one value. So when you get to the second one, you should see that it's second order with respect to the nitrogen monoxide and it's first order with respect to the bromine. So here's what's different in terms of the two of these. When you look at this reaction, okay, and if you're writing the value of K, the B value, the B concentration gets squared. But when you look at the actual rate law, based upon the experiments, B doesn't get squared, even though there's a coefficient of 2 in front of it. So what that means is that there's some hidden mechanism taking place that doesn't make it second order with respect to B. That 2 is there in terms of balancing the equation. But, and this is what we're going to get into later on, is that because you have that 2 in front of it, that doesn't necessarily mean when you're determining the rate law that that value is also going to get squared. So you can't look at the coefficients in determining the rate law and go, oh, there's a 2 in front of it, oh, that should be B squared. We can't do that. And later on you'll see why we can't do that. Now, when you get to the next one, where you have 2 nitrogen monoxides and Br2 turning into 2 Noble, in this situation, it is second order with respect to the nitrogen monoxide. So that 2 then actually does match up. Oh, we're going to square that. So in this one, what you would say, what you should see is that it's second order with respect to the nitrogen monoxide. It's first order with respect to the bromine. But then overall is what we call a third order reaction. So if you add those exponents up, it's actually a third order, okay? So if all goes well, that rate constant K should be something times 10 to the 4th. Okay, it should be a pretty big number, all right? On the questions off of the that photocopied sheet, make sure on 21 that every one of those should involve seconds at some point, okay? Every one of them has to involve seconds. When you get to 23 and you find that value of the rate constant, that should be, assuming that you left it in minutes, which seems reasonable, you should get a value of K of around 180, okay? And on 24, you should see that it's first order with respect to the iodine and that god-awful complex sulfur molecule. And on 27, because it all kind of builds off of each other, on 27, when you get down to D, and this is in micromoles per second, that rate on 27D would make a not so good GPA. Okay? Not so good GPA. Now,
What was the hit on 24?
on 24, then they were just, it was just first order with respect to each one of them. That's all you had to do is just find the rate law. That R value, that's all you had to find. So you should see that it's first order with respect to each. Morgan?
Did you say you want 23B in minutes instead of seconds?
Yeah, that's just because that's what it's in.
Okay.
That's the data that they gave you, so you just leave it like that. Okay. Anything from the studio audience? Going once? Going twice? So Morgan, stop that for a second, if you would. Okay, so here's where we're at right now. So we figured out the rate law. So they both have their place, especially in terms of what you can measure and what you can determine. So the rate law, how you figure out that one, is you do literally those experiments. You change the concentrations, you get things to cancel out, you see how that impacts the rate of the reaction, okay? Now, like the one you guys are gonna do with iodine has a very distinctive color. You all have seen iodine before, it's like reddish brown. So the lab that you all are gonna do, we're gonna take iodine and we'll mix it with acetone and hydrochloric acid. And it's a relatively slow reaction, okay? So what we can do is we can start and say, okay, here's the initial concentration of iodine based upon when we mix everything together. And then as the iodine gets used up, that color fades out, and it takes a while for that to happen. So then we can know, oh, okay, we know how much iodine we had to start with, and we know the iodine is in there because of the fact that it has a distinctive color. And then when the reaction stops, it goes clear because that means all the iodine is used up. Okay, so if we know how much concentration, what the concentration of iodine is at the beginning, and we know the final concentration of iodine is 0 because it goes clear, and we know how long it takes, we can figure out the rate. And that's what you guys are going to do in this lab. Problem is sometimes a lot of reactions take place very, very quickly, okay? And the other disadvantage of just your basic rate law is that it doesn't involve time. So I can't run a reaction and say, okay, hey, what's the concentration of iodine going to be after 5 minutes? If all I know is just the rate law, I know the rate, but I can't figure out what's going to happen over a certain period of time. So once you know the rate law though, then, and this is going through the calculus, then you can figure out what's called the integrated rate law. So with the integrated rate law, what this allows you to do is calculate concentrations at particular points in time, okay? So there's 3 types: 0 order, first order, second order. 0 order reactions happen, but they're very, very rare. But I do want to point out kind of this pattern that you'll see. So this is on your sheet, and on your equation sheet itself, there isn't anything about 0 order reaction. So if you specifically need like 0 order reaction formulas, I would give those to you. But I'm just going to kind of point out the pattern. So what you'll see that's common when you're doing the integrated rate law is that these have values that if you plot them become linear functions. Any linear function is y equals mx plus b. So all of these, that if you look at these, that don't look anything like y equals mx plus b, but they actually are. So if it's a 0 order reaction, what would happen is this, is if you drew a graph where you plotted the concentration of A versus time, what you would see is that the constant, and this is always based upon a reactant, okay? It's always based upon a reactant. So what happened is if you plotted the concentration of A as a function of time, you would see that A is the concentration of that reactant is decreasing as a function of time. So what you'll see also on all of these, that it's going to involve A naught. A naught is just the initial concentration. So this is the simplest in terms of seeing it as y equals mx plus b. Because all we're saying is that here's your slope, and the reason that negative sign is there is because, oddly enough, it's going to have a negative slope. So I don't want you to look at this and go, oh, that's a negative of a negative, okay? All I'm telling you is the k value, when you graph it, would have a negative value, okay? So don't look at this and go, oh, I'm going to take a negative of a negative. It's just when you find the slope, it's a negative value, because A is going to be decreasing. So A naught is your y-intercept. So this point up here would represent the initial concentration of A. Maybe it's 0.1, 0.2, whatever it is. So what would happen as a function of time, this concentration is going to decrease, right? And at some point it's going to go to zero. When it goes to zero, hey, guess what? The reaction is stopped. Okay? You have a question?
Mm-hmm.
Yes, ma'am.
So when you're saying like the negative, like not to get confused, so it's not little k, right?
Yes, these are all little cases.
So can that ever be a negative value, or it's always positive, right?
Hold on, whoa. What are you talking about? Big K or
I'm just
little-
confused, like, wait, why are you like saying not to get confused with taking a negative as a negative?
Because I've had kids ask that question. So when they calculate this slope, it's a negative value, and then they think they need to take like a negative
Okay.
of a negative. Okay? I'm just pointing it out. When you find that lowercase k, that rate constant,
It's just negative because...
yeah, it's just a negative value.
Okay.
Because the line's going to be coming down like this. Okay? That's what I'm saying. Don't overthink that and go, oh, it's a negative of a negative, which makes it a positive. That's not what we're saying. Okay? Now, if you look at the units, okay, and you absolutely have to pay attention to units, okay? If you don't pay attention to units, this thing is going to turn into an absolute train wreck, okay? So, because of the fact that this is just concentrations, you have, oh, that concentration of A is just going to be in molarity. The A naught is going to be in molarity. So the only way that I can add things together, oddly enough, is if I have this work out to be units of molarity as well, okay? Well, I can't add molarity to seconds, kind of a violation of mathematics. So if you look at what's going to happen, this time has to be in seconds, okay? The time's always going to be in seconds. So that means my value of K has to be molarity per second. So if I take my units of K, and there's a couple of ways you can view this. One is that K is going to be the slope of this line. Oh, that's change in Y over change in X. Oh, that's molarity per second. Okay, that's one way that I can figure out the units of K. The other way that I can figure out the units of K is that I have to take molarity per second to excuse me, I have to take molarity per second times seconds to get the seconds to cancel out. Therefore, I can take molarity plus molarity plus molarity. That's the second way that you can figure out the units of K. If you come up to the rate law itself, okay, just the rate law, oh, R equals K. Well, that's kind of cool. So that rate has to be in molarity per second. So therefore, K has to be in molarity per second. So I don't care how you figure this out, but it's all one big puzzle, okay? Everything has to fit together. So no matter how I view the units of K, whether it's the rate law, the integrated rate law, or a graph, I can't have one system of equations going, oh, K has this units, but another one says, no, 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 K has this units. Well, which one do I trust? I don't know. Flip a coin. No, everything has to work together. So this gets me units of molarity per second. This K here gets me molarity per second. So when I multiply it by seconds, I get molarity. If it's a linear function, it's the concentration of A versus time is a graph. Oh, that's changing Y, which is molarity per second, no matter what. So I can look at the slope of the graph, I can look at the rate law, I can look at the integrated rate law. Everything is going to lead me to the thought that on a zero order reaction, the units of lowercase k have to be molarity per second. Good with that one. Okay. Right. Now, let's move on to first order. Now, here's the weird thing about natural logs in terms of how we handle units. And this only happens with natural logs. This only happens with natural logs. Natural log, when you take the natural log of a value, its concentration, whatever it is, as soon as you take the natural log of anything, the units disappear. So when I take the natural log of the concentration of A, right away, this has no units. This is just a number, okay? So I had a kid, Joel Gaddy, hated writing down units, hated it with a passion. And so when he got to this part, I said, Joel, this is going to be your favorite function to graph, because you don't have to worry about writing down units. And so I started calling him Lenny, because Lenny was short for like natural log. So that was his nickname. Once we got done, this was like Lenny. You don't have to worry about units. Oh, score! Because he didn't have to worry about any units. So here's what's going to be important. This has no units, okay? Guess what? This has no units. So what has to happen here?
It has to have units?
It has to have no units, because I can't take no units here and no units here and add units to it, okay? So this can't have any units either. So here's the deal. So that time is going to be in seconds, right? So K then has to be in 1 over seconds. So when I take seconds times 1 over seconds, guess what? I don't have any units. So from this perspective, K is going to have units of 1 over seconds or s to the negative 1. Now, if you go up to the rate law, right? So look at this. If you just look at the rate law, R equals Ka. Well, R has to be in molarity per second. My K value then is 1 over seconds, because my concentration is going to be in molarity. So if I look at the rate law, ooh, that has units of 1 over seconds. Okay? Because that's the only way I can make my rate work out. Now, in terms of graph, with this one, again, this is nothing but y equals mx plus b. So this is going to be time, and this is going to be natural log of whatever that is. Now, once you actually start to see the numbers, you'll see that these natural log values are actually, when you take the natural log of these values, it's actually negative numbers. So it might go like -2, -3, -4, something like that. And this line is going to slope down here like this. Now again, here's the other way that you can view the units of lowercase k. This is going to be the natural log. What units is this going to have?
None.
Has no units. So if I look at the slope, I'm going to have no units divided by seconds. Units are going to work out to be 1 over seconds. Okay? So again, you can look at the slope, you can look at the rate law, you can look at the integrated rate law. No matter what, it's going to lead you to the idea that the slope is 1 over seconds. And again, this is a negative value because this line is going to come down here like that. So when I tell you that that slope for first order is a negative k, all I'm telling you is that the k is going to be a negative value. Okay, again, it's not a negative of a negative. It's just going to be a negative value. Okay, Alan,
Isn't that 1 over seconds times seconds, which cancels out?
what do you mean?
Because k is 1 over seconds and times
Yeah.
seconds.
Yeah, so I don't want any units. Because this, when I take the natural log of a, this doesn't have any units.
Oh.
And this doesn't have any units. So I can't have this ending up with units because I can't take a number here that has units and add it to something that doesn't have units. Yeah, I don't want any units coming out of this deal. Can't. Because then I couldn't add them together.
Okay.
Okay? Laura,
Wait, so what's the units of 0?
what do you mean?
I think my brain stopped working.
Where do you see, when you're talking about zero, what do you, zero what?
Like the K unit of 0? So tired.
So he has an order of 0, so we're talking about 0 is an exponent.
Are you talking about like the
The
concentration?
this A naught?
No, like. Never mind. I'm having trouble with that.
If you figure out what that zero is, let me know. Okay, so that's probably the most common, the two most common ones are gonna be first orders and second orders, okay? Now, when you see the pattern, oh, okay, well, let's talk about second order reactions. So if it's second order reactions, then you're gonna have 1 over A. So as soon as you take 1 over A, what units is that gonna be?
1 over molarity.
Yeah, into the negative 1, okay, or 1 over molarity, same thing, right? So if you look at the units, I've got 1 over molarity, or m to the negative 1, and then I take 1 over my initial concentration, which is also going to be m to the negative 1, which means this value here, this kT, okay, has to, oddly enough, produce units of 1 over molarity. So I've got seconds, right? So if I look at what units K has to have to get that, I can write that as 1 over molarity seconds. So now, if you look at what's going to happen, then if I take 1 over molarity seconds times seconds, the seconds cancel out. I get 1 over molarity, it's the same thing. So on this graph, if you graph 1 over A versus time, this is the only one that's actually going to produce a positive slope. All the other ones are going to be negative slopes, okay? So again, if you look at the units of the slope, that's going to be change in y over change in x, which is going to be 1 over molarity divided by seconds, which is the same as 1 over molarity seconds, okay? If you come up here to the rate law, you have molarity seconds equals 1 over molarity seconds times molarity squared. Boom, that cancels out. I get molarity seconds. So whether it's the rate law, the integrated rate law, the graph, all three lead you to the exact same units, okay? That's the big idea. Now you're going, well, great, Mr. Merkant, how do we use this in a lab setting? How do we do this? Well, let me show you. So how this plays out is that you're going to be given a data table like this, okay? Now, I actually I simplified this a little bit to expedite the process. So typically what you're given is this page of the data. you're going to say, okay, at time 0, we have this reaction where A is turning into B plus C. Just a generic, just simple decomposition. Maybe it's hydrogen peroxide turning into water and oxygen, okay? Water decomposing into hydrogen and oxygen, something like this, okay? So what we've done is that we've developed the capacity to measure the time. No big deal, we're gonna have a stopwatch. When you guys do this lab, you're gonna have a stopwatch and you go, boom, start, here we go, okay? So at time 0, when you start, you're gonna know the initial concentration of A. Then 50 seconds later, the concentration of A has dropped down to this, 0.00787. Another 50 seconds later, we're down to 0.00649. Another 100 seconds later, we're down to 0.00481. Another 100 seconds later, we've dropped to this. So all of these are going to be based upon the idea that you're starting with a concentration of one of the reactants. Okay? So it's always going to start with a concentration of reactants, and you're going to keep track of that as a function of time. Now, a couple of things that you have to be careful of. One is that don't assume that the first gap is 50 seconds. The second gap is another 50 seconds. But then they start going in 100 gap seconds. So when you're looking at that data, don't assume that the first gap of time is going to be the same gap all the way through. Okay? So just be aware of that. So in terms of what you would collect, this is it. You're going to say, here's the concentrations of these values as a function of time. So this is what you would be given. So here's the first thing that you would have to do. And I did this just to speed up the process. So what you would do is the first thing that you would have to do is punch into your calculator the natural logs of these values. Okay? So you would punch in, natural log of 0.01, natural log of 0.00787, natural log of this. So you would have to generate these values. Now, look at the trend. You're going from negative 4.605, and you're getting down here to negative 5.573. So when you're doing the natural logs, number one, these values are negative. Number two, the values are numerically becoming larger. Now don't flip out and go, oh, they're becoming smaller because they're negative values. No, this isn't a math class, okay? This is a bigger negative value, okay? Trust me. Boom. Negative sign just gives you negative. Okay? Then, to get your inverses of A, again, you would take your calculator and you would type in, I'm going to take the inverse of 0.01. That becomes 100. This becomes the inverse of 0.00787. So now, here's the trend though. Notice that these are becoming bigger negative values, okay? But these are becoming bigger positive values, okay? So that's what you will see as a trend. Because of the fact that you're talking a decrease in the concentrations, your natural log values are becoming bigger negative values, your inverse values are becoming bigger positive values, okay? Now, at this point, you can't tell anything. The only thing you have is this. So the only thing that you can do, and trust me, there is no shortcut. I promise you, like, when you walk in the door tomorrow, I'm not going to say, you don't have to do the whole graphing thing. You can just do this. I promise you, if there was a shortcut way to do this problem, I would absolutely tell you that right from the beginning, okay? So the only thing that you can do to figure out if it's a first order or second order reaction is to make a graph and see which one of these is linear. Okay, there is no other option. Okay, that's it. You have to physically draw the graph to see which one is linear. That's it. Only thing you can do. Now, when you draw the graph, there's two options. Okay, and it's a personal preference one. So one option is that, and some people like this. What you would do is you would come in here and you're going to draw your graph, okay? And you're going to, and you want to draw these as big as you can, okay? Because what you'll see is that sometimes the difference between the linear and nonlinear one is kind of subtle, okay? And if you don't have really good graphs, you can't tell which one is which, okay? So you're going to come in here and go, okay, I'm going to plot time along here, and let's say I'm going to put natural log. That was a horrible, I have no idea how that turned out to be an L. Natural log here. Now, when you do your natural logs, 0 is technically way up here, okay? Because you're going to go 0, -1, -2, -3, -4, okay? So if you look at this like -4.6, so what you might do is start your graph up here and go, okay, I'm going to make that -4.600. And then you want to end up here at like -5.5. So you're going to end up here at maybe like -5.600. And then you're going to spread that gap out over here. Then on your time, in this case, you're going to go from 0 over to, so there's like 100 seconds, 200 seconds, 300 seconds. So you're going to go, oh, at time 0, that's -4.605. Okay? So that's going to be your y-intercept. Okay? And again, this is just a linear function. Oh, that's my y-intercept. Then you're going to go to 50 seconds. And you're going to go, oh, that's -4 point whatever. 100, boom. Okay? 200, boom. 300, boom. And then you're going to draw that line. Okay? Now notice that this has a negative slope to it. Okay? So this is why I said that k value is going to be a negative value. Because when you find this slope, it's just going to be, mathematically, it's going to be a negative value. Yo, knowing this is algebra 1. Oh, a line comes down like that. Oh, that's a negative value. That's all that means. And when you find the slope, and sometimes you're going to have to draw like almost like a line of best fit. When you're finding the slope, listen to me. When you find the slope, the points that you pick to find the slope has to be on your line of best fit, okay? If your data points aren't on that line, you can't use that to find the slope, okay? So if you look at the units, you're going to do change in y over change in x, right? You're going to have no units on top. You're going to have seconds on the bottom. Your k value has units of 1 over seconds. Okay? So this is option number 1. You put the time, you put your natural log over here. Option 2, you're going to draw a separate graph of 100, 200, 300. Now you're going to plot 1 over a. So you're going to go with this one. So notice that these values are getting bigger. So you can kind of come in here and drew like the little squiggly lines, okay, to show that there's a gap, okay. So you can start this at like 100, and you're going to end up at about 263. So maybe go like 100, 150, 200, 250, 300, however you want to set up your scale. And then you're going to come in here and you're going to plot those points, and you're going to go, oh, there's 150 seconds, you're at 127, da-da-da-da-da, you get this line. So, one option is that you draw them as separate graphs. If you like that, and that makes sense to you, and you like that, do that, okay? And then you're just going to look at it and pick the one that's most linear, okay? And again, there is no shortcut, okay? There is not a shortcut. This is the only way that you can figure this out based upon experimental data. Now, the other option that you can do, and some people like this, I'm going to show you option number 2. So option 2 is you do this, okay? Now, what I did on this graph is that I only used one time scale. So I went 0, 100, 200, 300. And I put my natural log here, and then I put my inverse values over here. So the advantage of this is that a lot of times it's going to allow you to compare them and see which one is more linear. Some people hate this, okay? Some people hate on this, like, this sucks. I don't want to have to plot two different y-axes against the time. And it flips them out, and it's like, oh my God, I have to draw two separate graphs. Fine, draw two separate graphs. This speeds up the process a little bit, okay, because you only have to have one time scale, and you put your 1 over a here, you put your natural log over there. Don't care, okay? It's completely up to you, okay? But this is going to boil down to the quality of the graph. So if you look at this, okay, this graph here represents my natural log values. So I can look at this and go, it's not very linear, okay? It's pretty curved. Kind of starts off linear up here, and then it's not towards the bottom. But when I look at my graph of 1 over a versus time, and again, notice with this is much more linear, but even, look what I did. Even when I drew this graph, all of my data points aren't exactly on line. They're pretty close, okay, but they're not all exactly on the line. So when I found the slope of this line, and this is what I expect to see out of you guys, I said, okay, hey, here's my slope. I circled the points that I used, so that way, hey, I'm going to convey to you what I've done. Here are the 2 points that I picked. Notice I didn't pick this point because it's not on my graph, okay? I have to pick points that are on the graph. And this one just happened to work out. Don't think that I purposely picked this one because that's like at the intersection. It just happened to work out that way, that was an easy point to pick the x and y coordinates on. So here's this set, okay, times 0. I got 100. And then over here at 200 seconds, that's going to be 210. So notice that I spread this out as far as I could. Don't draw like tiny little postage side stamps. If you have really small graphs, you will never be able to see the difference. Because if I just crammed this into small graphs, I might not be able to see the difference between which one was linear and which one wasn't. So you always want to draw as big a graph as you can. So then I came here and I said, okay, here's my slope. I showed this, here's my change in y, here's my change in x, I get the units, 0.55, 1 over molarity seconds. That's my rate constant, okay? This isn't my equilibrium constant, this is my rate constant. Now I know what my value of k is. Now, here's the beauty of how you use this, is that now that I have this value, now I can do a couple of things. Now that I know, because of the fact that when I plotted 1 over a versus time, that's the one that's a linear function. That means that this is going to be a second order reaction. So if it had been natural log versus time, I would have known that was first order. Now, this is how I remember this. Because if you look at what you have on your equation sheet, on kinetics, all it has here on this kinetics is natural log of a minus natural log of a naught equals negative kt, and then 1 over a. They don't even tell you which one is first order and which one is second order. Okay, they don't give you that information. This is how I always remember it. Natural log, that L looks like a 1. That's how I remember that is a first order reaction. Okay? I don't care how you figure it out, just remember that. But again, notice on here, they don't give you the 0 order stuff. So if you ever on a test have to deal with 0 orders, I will give you those functions. Okay? And notice here, they technically didn't give this in like y equals mx plus b format. And if that flips you out, like on this one, just add the natural log of a naught over. Add the 1 plus 1 over a naught over. So if you really like it in slope-intercept form, it's a pretty simple manipulation. So what this means is that this is second order. So if I were to write, if you were to add, based upon this data, if you were asked to write the rate law, okay, and you have to pay attention. Are you talking rate law or are you talking integrated rate law? Since this is second order, and if you were asked to write the rate law, I would say R is going to equal K, which is 0.55, 1 over molarity seconds, and then times the concentration of A squared. So knowing this, and if I were to ask to write the rate law, this is what I would write. Okay? Now, the problem, and this is cool, right? But what this is going to tell me is the initial rate. It's not going to tell me what's going to happen later on. There's my rate law. Now, to write the integrated rate law, now that I know that it's second order, now I'm going to come here and I'm going to write this as 1 over A equals my K value, which in this case is 0.55, 1 over molarity seconds, times time plus 1 over A naught. Now, here's the beauty of this. Now you can work magic. So let's say you say, hey, I want to figure out what's the concentration of A after a certain period of time. Like let's say, hey, what's the concentration of A after 75 seconds? Oh, okay. I can take 0.55, 1 over molarity seconds, times 75 seconds, plus 1 over A naught, and if you go back up here, what was my initial concentration of A naught? Oh, that was 100. I can write this as just 100, because that's the inverse of that. Plus 100. So if I'm going to find, somebody do this. Take 75 seconds, multiply that by 0.55, add that to 100, and then to get the value of A, then I've got to take the inverse of that to actually get the concentration of A. So somebody take 0.55 times 75, add that to 100, and then take the inverse of that to actually get the value of A. What do you get?
7.1 e negative 3.
What'd you get?
7.1 e negative 3.
Times 10 to the negative third. Now remember that number, okay? So what that means is if I go back, remember that number, 7.1 times 10 to the negative third. So if I look at my chart, okay? So look at this. At 50 seconds, my concentration was 0.00787. At 100 seconds, my concentration was 0.00649. You have a value of what? 7.1 times 10 to the negative third? Notice that that 7.1 times 10 to the negative third fits within this data set. Okay? So if that number that you just got didn't fit within these two data points, I've done something wrong. Okay? So what this allows you to do is say, okay, if I know a certain value of time, I can figure out what my concentration needs to be. Or you can work backwards and say, hey, I want to know how long it's going to take for my concentration to reach exactly 0.0040. So now that I know the slope-intercept, I can plug in my known concentration, my initial concentration, and solve for time. So that's why the integrated rate law is so much more versatile than just the rate law is. Okay? Now, let's play the what-if game. If the natural log had been the linear function, okay, then I would write that as the natural log of A is going to equal, and I'm just going to make up a number, somebody take 0.4. Oh, and divide that by 100. That should be 0.0004, right? Okay. I just randomly picked a couple numbers. Now, this is where this gets mathematically a little bit tricky. If you're going to try and use this one, let's say that you want to, let's say you know the time and you know the initial concentration of A, and you want to find the concentration of A at a later point. How do you undo natural logs?
Take E to the power.
Exactly. So I just completely made up this number, rough estimate. So let's say that we're going to pick that time in 75 seconds. So if I want to do this, I take negative 0.004, 1 over seconds, times 75 seconds, plus the natural log of, what was my initial concentration? So somebody take, I have no idea if this is even going to work. This is completely random. But I'm just going to show you the process. So you're going to take the natural log of 0.01, add that to 75 times negative 0.004, and what do you get?
Negative 4.91.
Negative what?
4.91.
4.91.
1.
Okay, and this has no units. Okay, it has no units because these seconds cancel out. So then how am I going to find the concentration of A then? Oh, I'm going to take E to the negative 4.91. And that's how you would find the concentration of A at that point. Okay? All right. So let me hand out your assignment. So, Morgan, can you stop that camera for a second? So this is just a simple one. A is decomposing into B. And we're keeping track of the concentration of A as a function of time. Okay? So the first thing that you've got to do is go through and take the natural log of these numbers, take the inverses of these numbers. Then you're gonna draw two graphs. And I've got graph paper up here. So you need to decide how you want to do your graphs. Do you want to put them both, put one time and put natural log on one, inverses on the other, or do you want to draw them as completely separate labs? I care not. Okay? Just make them really, really neat and as big as possible. Then you're going to plot both of those, and then you're going to look at them and go, okay, is it first order or second order? Do the same thing here, and then 29 and 31. I'll tell you this, you should have 2 first order reactions and 2 second order reactions by the time you get done. Okay? So you're going to go through here, and when it's asking for the half-life, okay, so let me explain what the half-life is. And I've got the equations on your sheet. Half-life refers to how long it takes for the concentration to drop to half of the initial value, okay? So if you look at this initial data that we used, okay? So my initial time is 0.01. At time 0 it's 0.01. So my half-life then would be the time it would take for this concentration to drop to 0.005. So when I look at my data, I think I got to figure my half-life has to be somewhere between 100 seconds and 200 seconds, okay? Because that 0.05 is going to be somewhere in this range. So tomorrow we're going to go through, I just don't have time today. Tomorrow we're going to go through the actual process on how the half-life equations work, but they are on that set of notes, okay? It's just kind of a plug and chug thing to calculate that half-life. But you can look at it and go, oh, hey, does this make sense? Okay, I'm done. You're on your own. I know you two have to leave.
Yes.